All right, so let's continue with this video, focus on the orthogonal and orthogonal diagonalizable. So as we saw in the previous video, when you have a set, okay, with 3, 4, 5 vectors, so to show that the set is orthogonal, you first have to show that the norm of each vector is 1, and secondly, vectors are mutually orthogonal. Okay, we explained that in the previous video. Now in this new video, we want to continue with this concept of orthogonality, and if we consider an invertible real value matrix Q, okay, by definition, this matrix is orthogonal if and only if Q inverse is Q transpose, okay? So the inverse of this matrix should be equal to the transpose of this same matrix, okay? We can prove this, but I don't think it's worth it in this video. Okay? So I can give you an example of a matrix where you have to show whether it is orthogonal or not. Let me give you this. All right, this is an example of an orthogonal matrix, okay? By the way, this is a very famous matrix. So I want you to take 2 minutes. You can pause this video, take 2 minutes, and show that the Q inverse is equal Q transpose. You know how to find the inverse of the matrix. If you can't remember, please check some videos back, okay? If you know how to find the transpose of a matrix, I want you to take 1 minute or 2 minutes to find this quickly. And if you start, it is sure that this is an orthogonal matrix. So I just want you to double check this before we continue. And if you can't double check, if you can't find it, this means there is a problem somewhere in your working. So you have to go through again until you obtain this before you move on, okay? All right, let's look at this definition. A square matrix A is orthogonally diagonalizable if we can find a diagonal matrix D and an orthogonal matrix Q such that this formula is satisfied. This relation is very important because you can show that the matrix is orthogonally diagonalizable without this information, okay? Without using this formula. All right, having said that, let's also look at the symmetric matrix, okay? So a matrix is symmetric if and only if A is equal A transpose, okay? We all know how to find the transpose of a matrix. So a matrix is symmetric if A is equal A transpose, okay? Then let's look at this last part. This is a very useful theorem. The theorem says that a square matrix A, and this matrix is orthogonally diagonalizable, then it is also symmetric, okay? Let's prove this. We assume that D is equal Q inverse A times Q. All right, D is a diagonal matrix, Q is the orthogonal matrix, right? So when you say Q orthogonal, it means Q inverse is equal Q transpose. Then if we take this formula and we multiply the left side by Q, this is Q times D is equal Q times Q inverse times A times Q, okay? And we multiply the right side by Q inverse and Q inverse. This is what we obtain. So remember that Q times Q inverse is identity, and this is also identity, right? So this is just identity times A times identity. This is just a matrix A, okay? So we also know that this Q inverse is Q transpose because Q is orthogonal. So this is Q D times Q inverse or transpose. So let me rewrite it in this way. A is equal Q times D times Q transpose. Let's call this the first formula. Let's call 1. Formula 1. All right, let's take the transpose of this formula 1 and see. If we take A transpose, it is equal Q times D times Q transpose all transpose, okay? Remember that A times Q transpose is equal Q transpose times A transpose. So we have to flip the position, right? So it's the same here. This is Q transpose times D transpose. So we start with this one, right? As I said, we have to flip. We start with Q transpose, D transpose, and Q transpose. All right. Q transpose is Q. D is the diagonal matrix. So the transpose of a diagonal matrix, given that the non-diagonal elements are all zeros, then D transpose is D, and here we have Q transpose, okay? Let's call this formula 2. Then if we compare, of course this is 80. So if we compare the first formula and the second formula, then we see that we have A transpose is given by Q, D, Q transpose, and A transpose here is Q times D times Q transpose, okay? So this means that, so 1 is equal to, means that A is equal A transpose, okay? So this is the theorem. We prove the theorem. So if you have a question and you have shown that the matrix is orthogonally diagonalizable, so there's no need for you to show that that matrix is symmetric, because it's just obvious by the means of this theorem, it is symmetric, okay? So this is all for this video. Thank you.